So I would say there are three main things we can get from a mass spec, okay? First up, we can confirm the molecular weight of the compound. This is very useful if you make a new compound and you want to confirm that it is what you think it is. This is actually, you need a mass spec for each compound. When you publish a paper, you have to publish it with its mass spectral data, because if you use a big old mass spec, you can actually confirm the molecular weight to like 6 decimal places with accuracy to 6 decimal places. So this can be very useful. Certain atoms give unique mass peak patterns, okay? So this is unique to certain things in a molecule, and so if these certain peak patterns are present, we can use them again to confirm the structure, okay? Because if we think they should be there, then they should be there. Or we can also use it to deduce the structure. So let's say we have an unknown compound. Again, we can use these mass peak patterns to deduce something about the structure of that unknown compound. And then also certain atom arrangements give certain fragment ions. This is kind of like the unique mass peak patterns. But this is more so dealing with carbons, and up here I'm talking about other atoms. Okay, so certain atom arrangements give certain fragment ions, and again we can use this to confirm or deduce our structure. So again, we want to confirm, again, if our compound should have these things in it, then it should be present in the mass spec. Or if we have an unknown, we can use these mass arrangements to deduce the structure of the unknown compound. Alright, so first up, these unique mass peak patterns. Okay, so these are things that will be present in every molecule that has the thing listed. Okay, so for instance, this bromide. Alright, so every bromide has a molecular ion and a molecular ion plus 2 mass units, and these peaks will be present in a 1-to-1 ratio. So here's an example of a mass spectrum. Again, each peak corresponds to a different mass of our cations. Okay, so we detect the mass of those cations. Each peak corresponds to a cation of a different mass. Okay, you can see here, this is the largest peak. We call this the base peak of the spectrum. And all that means is we just took the ion of the greatest abundance, just set it to 100, and then everything else is relative to that guy. Okay, so he was just the peak of greatest abundance. That's really all it means. It can help us deduce some things, as in if this is the most common ion, then there's a reason for him to be there. But really just the largest ion, or the ion of greatest abundance, we just call that the base peak. Okay, so then over here, these are the M and the M plus 2 peaks that I'm talking about. Okay, does anybody know why we have an M and an M plus 2 peaks, and why they might have a 1-to-1 ratio in this spectrum? Hold on, let's label them. This is the molecular ion, so here's our M, and then this guy is our M plus 2. What does the M mean again, right? The molecular ion, this corresponds to the fact that this mass peak has the same mass as our original compound. Okay, that's what the molecular ion is, that the peak has the same mass as the original compound. And so just adding 2 units to that, okay, you can see that these peaks are present in a 1-to-1 ratio. M and M plus 2 peaks have 1-to-1 ratio in height. And again, this is indicative of a bromine. Does anybody know possibly why? It's kind of hard because you guys haven't seen this before. But this is because bromine is present in 2 isotopes. Okay? Bromine has 2 isotopes. Okay? There is bromine 79 and bromine 81. Can anyone guess what their natural abundance is in the world? Maybe about 50-50. Okay, so if our molecule has this bromide, it's going to correspond to this mass, whereas if it has the heavier bromide, it's going to correspond to this mass. Okay, right? So they differ by 2 mass units here, and that's why we get 2 mass units difference of our molecular ion and our M plus 2 ion, and that's why they're also a 1-to-1, because these guys are present in a 1-to-1 ratio in nature. Okay, so again, they just correspond to the different bromines in our sample. Okay, so this compound has a bromine in it. That's why we have an M and an M plus 2, about 1 to 1. And we can see that this actually repeats as well. Okay, here's again one other 1 to 1 ratio. So again, this ion then has a bromide in it. Okay, so again, these are indicative of bromides. Okay, we're going to have our molecular ion and an M plus 2 peak, each with a 1 to 1 ratio in height. Okay, this is indicative of bromide. What are some possible structures of this guy? Let's think about it and let's see what we can deduce. Okay, so if we know we have a bromide, okay, bromide has these two masses, 79 or 81. So let's take the lower one. So M equals 156 minus the bromide, which equals 156 minus 79, and we get 77. Okay, and then what you can do is use the rule of 13, okay, to figure out how many carbons. To figure out number of C's, use rule of 13. Which is pretty much you just take your mass and divide it by 13. Okay? And the number that comes out is usually the number of carbons that are possibly in your sample. Okay? We use the number 13 because it corresponds to CH groups, right? C is 12, hydrogen is H. So if we use 13, it just gives us a rough estimate of the number of carbons that could be in our sample. And if we do this, we get 5.92, which is about 6 carbons. So let's see if this makes sense. If we have 6 carbons, then we use the molecular weight of carbon, which is 12, and we get 72. Okay, so 72 mass units correspond to carbon of our 77 that were left. Okay, 77 minus 72 equals 5. Okay, so we have 6 carbons. Here's our hydrogens, and we have a bromine, C6H5Br. Okay, and this corresponds to then, if we could imagine what it may be, probably this. Okay, this is definitely very hard. Again, what I want you to take from this discussion is the looking for the M and the M plus 2 ions being 1 to 1 ratio. And then from here, we can possibly figure out the number of carbons by using the rule of 13, which is simply divide the leftover mass units by 13, and we can get a rough estimate of the number of carbons that are possibly in our sample. Then we take the mass of the carbon to figure out how many mass units are left again. Okay, we have 72 mass units for carbon, so 77 that were left minus 72, we get 5, so C6H5. Okay, again, the main point here is that a bromide will have a molecular ion and an M plus 2 peak with a 1 to 1 ratio. Chlorides now have an M and an M plus 2 peaks with a 3 to 1 ratio. And so that's around here. Okay, just like here where we had the bromides, again, this be due to the different isotopes that are present in nature. The same is true here for chlorides. Okay, 3 to 1 ratio. And this is because we have 2 chlorides. It's 35 and 37. Different isotopes of chloride, and can we guess what they're present in nature, their natural abundance? Again, about 3 to 1. 3 to 1 abundance in nature. So again, this ion here, which is our molecular ion, here's our M plus 2. Okay, this guy has the chloride ion of lighter isotope. And this guy is our same compound, but it's got the heavier isotope of chlorine. So that's why, again, we are separated by 2 mass units and we are present in a 3 to 1 ratio. And again, we can see this repeating. Here it is, 3 to 1 again. So again, this ion will also have the chlorine in it. Okay, so the M and the M plus 2 are present in a 3 to 1 ratio. I'm not even going to go through and deduce the possible structure because it's not worth our time. Alright, iodines, okay? How can we tell that we might have an iodide in our sample? Well, the I plus ion is present at an M over Z, or a mass of 127. Oh, look, here it is. Okay, this means we have iodide. Okay, here is our molecular ion. It's also our base peak, you can see as well, because it's the largest peak on there. So it just so happens that our molecular ion is also our base peak. Okay, let's think about the structure of this guy. Okay, so again, our molecular ion equals 156. So let's subtract the mass of the iodide, which has a mass of 127, and we get 29. Use our rule of 13, and we get about 2. It's 2 point something, 2 and a little amount. So we have 2 C's, number of C's. So let's use this to see how many mass units we have left now. Okay, 2 times 12 equals 24. Okay, so we had 29 left to begin with. 29 minus 24, we get 5. Okay, so this could correspond to a C2H5I. What could this structure be? Really simply, there we go. 2 carbons, 5 H's, iodide. Nice. Okay, how do we know we have a nitrogen in our compound? Well, we will have an odd M plus mass, M plus, our molecular ion mass, and then some even fragments. So we can see that here. Here we have an odd molecular ion. Okay, and then we have some even fragments. Okay, this is because we have a nitrogen in our sample. Alright, so let's again try and maybe look at this structure. Well, if our molecular ion equals 115, let's subtract our nitrogen. Minus N equals 115 minus 14, and we get 101. Alright, let's use our rule of 13. And we get about 7. Okay, then, so this is our number of carbons. So 7 times 12 equals 84. Sweet. We had 101 left. 101 minus 84 equals 17. Okay, so again, what's ever left over, these are hydrogens, H's. So we've got C7H17N. Nice. Okay, so again, those are the unique mass patterns. There really are, that's about it. Okay, so again, molecular ion M plus 2 in a 1-to-1 ratio, bromide. 3-to-1 ratio, 3-to-1 ratio, chloride. Okay, when we have 127 present as its own peak, it could mean that we have an iodide. Okay, and when we have an odd molecular ion but even mass fragments, then we probably have a nitrogen. Alright, so those are the unique mass patterns. How about some common fragments? Okay, on to common fragmenting. And so again, these are kind of unique mass patterns that will indicate something about the structure of our compound. Okay, first up, if we have the loss of H2O in mass, we probably have an alcohol. Okay, and so we can see here they've denoted the molecular ion for us, which obviously would be hard to find yourself. I would have to tell you guys that. But here is the M-18 peak. We can see that it's pretty major. And so why is the number 18 so important, right? Because we have the loss of water, H2O, which equals 18 grams per mole. Right? Oxygen is 16 and each hydrogen is 1, so this is 18 grams per mole. So we lose 18 and we have the loss of water. Okay? Loss of H2O. So when we lose 18, which means the loss of H2O, it means we have an alcohol. Okay? Because that's what likes to fragment off, is water. Okay, of an alcohol. So this corresponds to this structure, and I definitely would not ask you to do this entire structure, but I would expect you to say, hey, we lost 18, this corresponds to water, so we probably started with an alcohol. Notice too, here's the other base peak, right? Here's the base peak, the largest peak, and we've lost water here as well, but we've also lost 15. What could that correspond to? We'll see on the very next example, and that's with alkanes. Okay, the alkanes, loss of CnH2n plus 1. So for instance, if we lost one carbon, okay, we would lose, so EgC1H2n plus 1. If n equals 1, 2n plus 1 equals 3. CH3, which corresponds to 15. Right? Again, carbon equals 12. Each hydrogen is 1. So 15. Okay, so we lost a methyl from that previous example. And so this is common for the alkanes. Okay, I'll show you what I mean. Here's our molecular ion. Okay, they've denoted it for us. And it is usually the furthest peak to the right. It's commonly the furthest it's still usually. But I would probably have to show you guys the molecular ion, or at least denote it for you, because sometimes it is hard to find. But it is usually the furthest peak to the right. Okay, if we correspond to 86, if we use the rule of 13, okay, 86 divided by 13, we actually get 6.6, and I would round down. It's another little tip, round down equals 6, and so 12 times 6 equals 72, so then 86 minus 72 equals, why can't I find it, 14? Yes, kids do that math easily. Okay, so this corresponds to C6H14. So this actually fits, remember way back when we learned the common formulas for normal alkanes, normal saturated alkanes? This corresponds to hexane, because it was CnH2n plus 2. Okay, so this corresponds to hexane. Okay, so here we've lost 15 mass units, here we've lost 29, 43, and 57. Notice how they kind of go in around loss of 15, but like 29 here, then here we've lost 2 carbons, because if we use the same formula, C2H2n, so that would be how many hydrogens? So if this is 2, C2H5. Okay, so here we lost CH3. Here we're losing C2H5, which is also an ethyl group. Ethyl. Over here is methyl. Can anybody guess what the loss of 43 probably is? Lost C3H7, or a propyl. Okay, so if we drew out hexane, CH3, CH2, CH2, 4, 5, 6. Okay, if we chop off this last methyl group here, we get a mass of 71, which corresponds to this guy. There we go, we lost a methyl. If we lose an ethyl group, okay, it chops it off right there. This corresponds to 57. Look at that. Again, that's because we lost this ethyl group all the way over here. We lose 3 carbons, we get 43. Look at that. And we lose 4 carbons off of here, we get 29. Okay, so this is the different ways that hexane can fragment. Again, we are bombarding our sample with a ton of electrons, so it can fragment in all these different places, give rise to different cations, and we can detect those cations in the mass spec. And again, these are all, again, they lose the mass corresponding to this formula, and so we get loss of 15, loss of 29, loss of 43, and each one of these corresponds to another carbon being lopped off. Okay, here's another example. You can see here we've lost 15. Okay, so lost, what does this correspond to? A CH3, Okay, but look at this base peak here. The highest abundance of the most abundant ion. Okay, it's a loss of 43. What does this correspond to? Remember 43? Propyl. Loss to propyl. Why could we lose a propyl as the main base fragment? Well, what if we had something like this? Okay. It's possible that we have this structure because when we think about the different ions that could fragment into, okay, we could lose a methyl group easily, for sure. Okay, this has a mass of 71. This gives a nice secondary carbocation. Another way to get a secondary carbocation, though, would be if it were to fragment this way. Okay, so this whole part kind of get lopped off. We get a nice secondary carbocation. It's a stable carbocation and stabler carbocation, and this corresponds to a mass of 43, which is again why it may be the base peak, because its cation is pretty stable. Okay, so we can use this, again, this is a more stable secondary carbocation. We can do that and use this analysis for other things. So here you can see this was a loss of 29 units. Okay, what does this correspond to? Go all the way up here, loss 29, ethyl, 29, ethyl. Okay, this mass spectrum actually corresponds to this structure. And so the base peak, the loss of an ethyl, actually makes sense if we think about the carbocation that we can form. Okay, because if this fragments in this way, okay, we just lop off that ethyl, we get this nice allylic carbocation. What is this stabilized by, everybody? Resonance. So this is a stable carbocation, so it makes sense that we would lose that ethyl as the most common ion. Okay, this has a mass of 55. So it makes sense that this is our most common ion because it's very stable. Okay, so again, the main things to take from this are those unique mass patterns. Remember, bromide has a 1-to-1, chloride has a 3-to-1, N plus 2. Okay, iodide has the 127. Nitrogen has an odd molecular ion with even fragments. And then with an alcohol, we lose water. And with the alkanes, we lose one carbon at a time. Okay, so that's mass spec. All right.